These notes are on why cells are so small. So when we look at organisms, we just finished up with mitosis and we saw that in order for organisms to grow, their cells are going to divide. So while you do have some single-celled organisms, those organisms are really, really small. And so cells are really tiny. So why are they so small? When an organism grows, why do we need millions of cells instead of just having one big, gigantic cell? So first bullet point, as you increase the volume, the surface area does not increase at the same rate. So when we look at a cell, as it gets larger, its volume is going to increase and its surface area is going to increase, but they don't increase at the same rate. The volume is going to increase at a much faster rate. So as it's getting bigger and bigger and bigger, the surface area doesn't get nearly as big. So you need to know this, surface area to volume ratio decreases as cell size increases. So here, as we have a cell, as the cell gets larger, the surface area to volume ratio is going to go down. And I'm going to discuss with you how to find the ratio, okay? The smaller a cell is, the more efficient it is at transporting materials across the membrane. So smaller cells are more efficient at transporting materials across the membrane. So let's look at this example. So let's say that these are trash cans, and so here you have one person. So in this cube, the person represents the volume. The volume can hold one person, and the surface area is the membrane. And so this is where the trash can is going to be located. And so for this particular setup, we have 4 openings, or we can say we have 4 trash cans, and we only have one person. So for every one person, you have 4 trash cans where we can deposit some waste. As we increase our size, we notice that we still only have 4 trash cans, but now we've increased our people. And this is because our volume has increased enough that we can fit more people. But for this scenario, we still were not able to fit as many trash cans because our volume increased at a greater rate than our surface area. So when you look at our ratio, we have 4 openings, we have 4 people, so it's a 4-to-4 ratio, or you can say it's a 1-to-1 ratio. We're going to increase our box even larger, and now we still have the same number of trash cans because we really did not increase the surface area that much, but we did increase the volume by a lot. And so now we have 4 openings, but we only, we have jumped up to 12 people. So our ratio is 4-to-12 for this. So let's look at the math. In the first scenario, we had a 4-to-1 ratio. The second cube, we had a 4-to-4 ratio, and then we had a 4-to-12 ratio. For each of these, the box was getting larger and larger. What we want to do is we want to be able to compare these. Now, these are a little bit easier because they all have 4s, and these are kind of numbers that we're familiar with. But we want to reduce all of these to their lowest form. And we want to reduce them so that the volume equals 1. And this way we can compare. So to do this, we're going to divide both sides by the volume. In 4-to-1, the volume is already 1, so it's reduced, so we don't have to do anything else to it. In 4-to-4, you'll divide both sides by 4. That gives us a 1-to-1. And then in the last one, we're going to divide both sides by 12 because remember, we want the volume to equal 1. So here we have 0.33 to 1. So now we're going to compare these volumes, the surface area to volume ratio. So when you compare, since the volume is 1 for all of them, then all you're having to do is look at the surface area. The higher ratio is more efficient. So 4-to-1 is higher than 1-to-1. It's also higher than 0.33 to 1. So our 4-to-1 is better. it's going to be more efficient at getting things across. And remember, this was our smallest cube. Okay, so let's work